good shot? Okay, good. I look good today then? That's good. I brought my beauty and not my brains. Today what we're going to be doing is integration. I absolutely love teaching the integration topic because I feel like most people at this level like it better than derivatives. So I kind of look at my people that are taking AS level, they're giving me dark eyes. I mean, because as we get further into it, integration gets more complex, but at this level, no, they still don't want, never mind. I think it's good stuff. Anyway, what we're going to be doing today is just learning the basics of it. Second period really didn't even think about taking notes on it. They just kind of watched. But you're welcome to take notes on it. It's good stuff. So we are going to start with what I feel would be a really easy part of this problem. I want us to draw y equals x squared, y equals x squared plus 4, and y equals x squared minus 1, all on the same graph. Oh boy. Integration has, I should write the what it is. We're doing integration. If you were drawing x squared, hopefully it looks as gorgeous as the one that I'm about to do. Yeah, wow, look at that. Nice. Very nice. Yes. Did you draw it just like mine? Are they perfect like mine? No? Well, you could aspire to be an artist like me. All right, so are we cool? So far, are we cool? Okay, so having said that, I am going to have us take each of these and I want you to find dy dx for every one of them of x squared.
2x.
Oh yeah, feeling good about that. And the derivative of x squared plus 4.
2x.
Ah, wow, that's nice. Also 2x. And then the derivative of x squared minus, okay, 2x. Let's talk about why in the world is this indeed true. What is the derivative actually giving me? What is it like? What is the derivative doing? Literally, when I take a derivative of something. It is finding the blank of any point on that. Slope. All these words are flying at me. Chain rule. Slope. Yes. It's finding the slope. And let's visualize this for a minute, okay? So x squared, this guy right here. What is the slope right here? 0. Are we cool? What is the slope at any point on this particular curve? And if I go down, what are the slopes? Negative. Negative, yes. What are the slopes over here? Indeed. All right, are we cool? What about moving up here? Do the slopes change? Well, what's the slope of this? Again, 0. And what about going down here? Also negative. And over here? Yes. And then one more. Here? 0, negative, positive. So literally when I take a derivative of something, it allows me to figure out the slopes of any point on that given curve. Is everybody cool with what I just said? Having said that, it is very obvious that they are not the same graph, but they are visually, physically the same graph that's been moved up or down, okay? So what we do with an integration, is we are able to start with this and move our way back to the original, okay? So it's literally the opposite of a derivative. So derivative, we find the slopes on any graph. Given the slopes on any graph, can we find what the original looked like? Okay, so that's what we're going to be doing. What is the name of the rule that we utilize to get from here to here? Does anybody remember? Power rule. Power rule. Very good. The power rule says to do what? Like in words, what do we do with the power rule? We take the exponent and do what with that? We bring it to the front and do what to it physically? multiply, right? So I take the 2 to the front, it becomes something that we're multiplying. And then I rewrite the x, and then what do I do to my exponent? Subtract 1. So if I'm doing the complete opposite, I am trying to go back to the original. Let me show you the symbolism that we're going to use. That tells me we are going to integrate. It's an elongated S. It looks like an S, but it's very long, okay? That's the symbol for take an integral, all right? And if I have something that's visually looking like a power, okay, the reverse power rule is going to allow us to take the integral. So the actual answer to this is, whoops, not that, I lied. It's going to be this over this. And let's make some heads or tails of this. When I took a derivative, I brought the 2 to the front and multiplied it to the x and subtracted 1 whole. When I'm going back, reversing it, what am I doing to the exponential power? I'm adding 1. What did I do when I took a derivative? I subtracted 1. So it's opposite. So I add 1, and then I took that exponent and I brought it to front to multiply. Now what's happening to that exponent? I'm dividing by it. Again, the complete opposite of what I did for the derivative. Okay? Come on in.
Hello.
Hi.
We have more letters.
Yay! Neat. Let's do a couple examples. If I want to integrate x to the third, what will it be? Go ahead.
X to the power of 4 divided by 4.
Yes. Add 1 whole and divide by that puppy. Are we cool? Let's do another guy. X to the divide by. Are we cool? How do we handle this? Oh. How do we handle a number when I'm taking a derivative? I make that number that's in front do what? If I'm deriving? Make it go for the ride. Same thing here. You're going to take that 2 and say, okay, that's part of the process. I'm just going to bring it for the ride. Now, what is the integral of x to the 4th? Over, and that's your new answer. Are we feeling okay? The 2 went for the ride. We do that. Let me make it really exciting. I know. I know. Yes?
Would it be x to the 3 halves or over 3 halves?
Yes. Can you tell everybody in the audience how you did that?
Because the square root of x would just be x 1/2.
Yes, you rewrite it first. Stunning. Let's keep going. You tell me it was x to the 3 halves over 3 halves. Can I leave it like that? Yes. Could I clean it up if I wanted to? Absolutely. What would that denominator do? If I divide by a fraction, I can do what? Not cancel it. Yeah. Multiply by the reciprocal. Take that reciprocal, bring it up, and multiply by it. Are we cool? Do I have to? No. Is it easier to play with later? Yes. Okay. All right. How do we feel so far? We're feeling good. Now, back to the beginning where I drew those lovely, lovely pictures. We obviously know they are gorgeous, however they are shifted up or down depending on the original, yes? Come over here. I would like you, please, to take the integral of this. Well, let's discuss. What is the integral of dy dx? What do you think? Y, that's correct. It goes back to the original. So it's going to be y equals. Now I would like you to integrate 2x, please.
2x squared over 2.
2x squared over 2, which reduces to
X squared.
x squared. Yes. Do this guy for me.
Same thing.
Ah. Okay, we got a problem. What about this guy? Also the same thing. However, do we understand that they were not the same thing when we started? There's an issue, right? So the dilemma is when I'm taking an integral of something, I don't know where it's located on the y-axis. It could be +1, it could be -3, it could be the regular guy. I don't know. So the way I handle it is back to the actual formula. The formula was add an exponent and divide by it, right? But I don't know where in the scheme of things it's located, so I'm going to put +c at the back end of it. Okay? The +c at the back end of it means it could have been +0, it could have been +4, it could have been -1. I just know that it's somewhere on that y-axis. It could be some version of that shifted graph. Is everybody cool with what I just said? And here's how we handle that situation. Okay, so we started with, let's just start with the integral of dy dx equals the integral of 2x, okay? We just did it, so it's not a surprise. What do I get when I do this particular integral? I get, what's this guy over here? Y equals, and what would this guy be? X squared, and now that I know that I'm not certain where it's located, I'm going to put +c. And then what's going to happen is I'm going to say, in this particular instance, my graph actually went through the ordered pair 0, 4. Okay? What does that tell me? It tells me a point on the graph that that original equation would have hit. Having said that, what does 0 represent? X. What does 4 represent? If I have an X and a Y, can I figure out what C is? 100%. I could take them, I could plug it in, I could solve. Oh, that went well. I could solve, and in this case, in this instance, what was my C equivalent to? C is indeed 4, and then what I do is I just rewrite this. My formula that I started with would have been the x squared plus 4. So I'm telling you, it goes through that specific x and y so I can figure out which version of that graph we would have started with. Are we cool? Yes, no, maybe so? What do you guys think of integrals so far? Everybody loves it. No, I know, it's so quiet. Is it because it's Friday and everybody wants to be sleeping anyway?
Yes.
Yeah, I get it. I get it. All right, let's do one. I got another one I want you to try. I want us to integrate it. Good luck. What do I need to do with this 1 over x squared? I need to flip that puppy out. Why? Because I can't take a derivative, nor can I take an integral of something that's in a denominator. That's a no-go. That's a no-go. So, what is the integral of dy dx? Y. What is the integral of x to the -2? X to the over. And then one last thing. Plus c. How many put plus c? Yeah. If you put plus c, you're cool. If you didn't, you lose a point. Guaranteed lose a point. Guaranteed. All right, how do we feel? Can this be cleaned? X to the -1 over -1? How can I make it look prettier? -1 over x. Beautiful. Yes. The negative can be on both pieces, so I'm just going to stick it out front. And then I'm going to flip that exponential power down to change it from its opposite sign. What do you guys think? Are we cool or not? It is really hot in here, yes? Or is it just me? It's just me?
No, it's
Oh, good, phew. Well, I know, but I mean, it could be just me. At this age, it could be just me. Okay, now, got a question. Oh, I do have a question. Let's see if you guys can reason through this. What do you think f prime of x means? A derivative is done. Also known as dy dx. Also known as y prime, whatever, right? Okay. I'd like you to find the original function. That means I want you to integrate. All right, see how that works for you. I think the first thing I'm going to do is I'm going to rewrite it, right?
4 is x equals 0.
Are we cool? Yeah? Do we remember to rewrite it? Because you can never, never, ever, ever take an integral in a denominator. It's a no-go, okay? So, I integrate this. The 4 goes for the right. I add 1 whole. I divide by it. Over here, I take the -2 for the right. I add 1 whole. I divide by it. And here's the new guy. How many x's are up here? And if I add 1 whole to it, I get one of them, right? So this is 4x to the 1 over 1, basically. Do I have to put the ones? No. I just want you to see it. So the moral to that story is if I have a constant, a 4, a 3, an 8, what do I do when I'm integrating it? I attach an x to it. So it would be 4x, or 3x, or -8x, whatever those numbers are. Are we cool? Plus c. And did we remember the plus c? Say yes if you did.
Yes.
Yay. How many no's? All right, clean her up. X to the 4th plus 1 over x plus 4x plus c. How'd we do? Yes, yes, question.
Shouldn't it be plus 2 over x?
Yes, good catch. It's so good to be smart, unlike myself. Thank you, I appreciate you. Good job, good job, good job, good job. I just didn't like the 2 today, so I got rid of it. Yeah. All right, are we cool? Yes, no, maybe so? No, yes. Do you like it? No?
Like it better than what we did.
A lot of people like it better than derivatives, yes.